So Professor Philipp Rachel is director at the Max Planck Institute for the Science of Light in Erlangen, Germany, and holds the Krupp Chair in Experimental Physics at the University of Erlangen, Nuremberg. His research interests range from the behavior of light in periodically structured materials to nonlinear optics, waveguides, optical fibers, and their applications. He has over 600 publications and in his co-inventor on 37 disclosures or patents covering many aspects of photonics. He is a fellow of the Royal Society and the Optical Society of America and has won several international awards. So with these few introductions, I would like to request Professor Philipp Russell to take over these sessions and start his lectures. We are very much eagerly waiting for your to listen from you. Thank you very much.
Okay, thank you for the nice introduction. Can you hear me?
Yes, perfect.
Okay. Well, do let me know if you can't see my screen or something goes wrong. First of all, thank you very much for the nice invitation. I haven't had a chance to visit Warangal, but maybe I will in the future at some point. And as was mentioned, I'm based in Germany, in a place called Erlangen, where we have a relatively new Max Planck Institute for the Science of Light. And one of the things we've been working on a lot for since the foundation of the Institute is photonic crystal fibers. So, but let's get straight into the talk. I've got a number of topics. I'm going to touch on several topics. So without going into great detail into any of them, I'd like to give you a kind of flavor of the kind of research that's been going on recently in my group, particularly in this field. Now, the fibers themselves, you can see on the screen, these are four main types of fibers. The very first one that we made at my group in Southampton and Bath in the UK back in the early 90s is the solid core PCF with an array of hollow channels running along its length and a solid core in the center. The next one that came along a couple of years later is the Holocore photonic bandgap fiber, in which the light is confined by a full two-dimensional photonic bandgap. And then at the end of just in 2002, we discovered the Kagome anti-resonant reflecting holocore fiber, which guided broadband light, which was unexpected because compared to the bandgap case, that was something we didn't see in the photonic bandgap case. And then more recently, there's been another kind of little mini revolution in the field, which are these very simple, we call them single ring anti-resonant reflecting holocore fibers that a number of groups have been working on recently. So I'll talk a little bit about most of these and some of the applications of them, of course, mostly focusing on applications. I'll talk a little bit about the holocore fiber at one point, but mostly it's about applications. So the first thing I want to tell you about is work that we've been doing on the solid core fiber. That's to say the one on the left here, which is a solid glass core, and in particular how you can use a fiber like this for high harmonic mode locking of fiber lasers. So this is work where we view the solid glass core as a kind of quartz oscillator, and we use optomechanical effects to light-driven optomechanical effects to mode lock a fiber laser at a high harmonic of its round trip frequency. So just to introduce this, if we think about a photonic crystal fiber with a very small core, order a micron or so in diameter, with a large air filling fraction, so these are large hollow channels compared to the size of the core, then the optical mode is very well confined in the core, of course. And if you have a train of pulses coming along, this train of pulses, if the frequency is correct, it's able to excite an acoustic resonance in the core. And the frequencies are typically in the gigahertz range. Now, the nice thing about these large hollow channels is that the acoustic energy is very well confined in the core. So we have close to 100% optoacoustic overlap in the PCF core, which enables all kinds of new things that you can do with this in particular. mode locking of fiber lasers. So let's just first of all talk a little bit about harmonic mode locking. This is mode locking at a high multiple of the fundamental mode locking frequency. If you try to do this in a ring laser and you just turn up the gain, you can get a lot of pulses, but they tend to be randomly spaced and they're very unpredictable and it's very noisy. It really doesn't work very well. The saturable absorber that one uses to get mode locking, it's unable to control the pulse shaping. There's nothing in the system that would kind of synchronize the pulses at a high harmonic. You can also, you could think about doing active harmonic mode locking, of course, which is the other approach, using an electro-optic modulator to control the pulse spacing. Now, of course, in principle, this works, but in practice, it's actually very difficult to get it to work well because you have to have very precise timing between the electro-optic modulator and the pulses. What we've been doing is exploring the use, as I said, of the acoustic vibrations in the core to kind of keep as a kind of metronome, if you were a control clock, for keeping the pulses in exactly the right time slots as they go around the cavity. So this is a fully passive system. It's self-stabilized and so on, as I'm going to explain in a moment. So we have a gain fiber, we have a saturable absorber, as you'd normally expect in a soliton type of ring laser, and we have a length of PCF within which the acoustic vibrations occur. And if you have a look in a little more detail at what's going on inside the PCF, we have the acoustic vibrations that might look like this, and then we have the pulses. The duration of the pulses is a picosecond or less. And they sit, each of these pulses sits in one of these acoustic time slots, and the time slot is about 0.5 nanoseconds in the typical case. So, okay, so this is what the system looks like. So, but why is it that the pulses are able to sit stably in the same position in the time slots like this? So what makes them so well behaved? Well, I mean, there are a couple of things here. The two main things, first of all, let's talk about how the pulses can actually be stabilized. Well, if you imagine a pulse, so this is a short pulse, and this is the acoustic vibration in time. If the pulse is sitting on the acoustic wave, so it's kind of surfing the wave, so the pulse is surfing the acoustic wave, it's sitting at the same point on the acoustic wave, then underneath the pulse, you can see the refractive index is increasing. So there's a change in refractive index underneath the pulse. There's a slope in refractive index underneath the pulse, and this creates a redshift. So the pulse will continuously shift towards lower frequency because of this slope in the refractive index. This only happens on the left-hand side of the. If you go to this side, it's the opposite way. It'll be a blue shift, but there's a red shift here. And then if we also think about the gain spectrum of the fiber amplifier, if we're sitting on the low frequency side of the gain peak, then the pulse, the higher frequencies in the pulse see higher gain, and the lower frequencies see lower gain. So there's a spectral blue shift caused by the imbalanced gain. And this blue shift and this red shift can cancel each other out to give you a stable frequency of the pulse, so the pulse frequency doesn't change with time. So this is just depicted over here. We have a blue shift in the amplifier, and we have a red shift in the acoustic vibrations, which can stabilize, at least in principle. At least you can cancel out the two effects. But the next thing, of course, to think about is why is it stable? I mean, you can balance those two shifts, but it doesn't mean that the system is stable. It turns out it is actually stable, and the reason for this is explained in this plot here. So this is now the relative position. So this is space, z minus vg naught t, so moving with the pulse. And the pulse is sitting here at a certain position. This is the point where the blue shift and the red shifts cancel, so the pulse would sit here. But let's suppose it gets perturbed and moves towards the right here, so it moves to the wrong position. It isn't in exactly the right place. Well, then the acoustic wavefront gets steeper as we move down here. This causes the red shift to increase. It reduces the frequency of the pulse, And because of the group velocity dispersion, the lower frequencies travel more slowly. So we get a drop in group velocity, and this pushes the pulse back to its equilibrium position. And the same thing happens in reverse on the left-hand side. It gets pushed back. So we have an automatic stabilization of the pulse position. So if there is any jitter, temporal jitter in the position of the pulse, the pulse always gets pushed back to the correct position, which is kind of a nice aspect of the system. It actually works very well. This is just one result from quite a few different results that have come out of the work in recent years. This is a laser that runs at 1.87 gigahertz and is a soliton erbium laser, ring laser. It's by using a stretch soliton kind of approach, where the spectrum is chirped different parts of the cavity, you can actually get down to pulse durations of 83 femtoseconds, so sub 100 femtosecond pulses. It's extremely stable. It can run for days, weeks without any drift. Okay, I do have a PDF, by the way, of these slides with references listed and so on, which I'm happy to send to you at the end if you'd like to have a copy of that. It'll have all the references and some explanations and so on, and pictures of the slides. So next topic is something completely different, and this has to do with the fibers themselves. And this is work that we've been having a lot of fun with. It's a novel kind of optical fiber which doesn't have any core, and yet it manages to guide light. And this happens because the fiber is chirally twisted. So we have a kind of chirally curved periodic space within which light is trapped. So I'm going to try and explain to you how this works. First of all, let me show you the result. So this is the PCF on the left that we're working with. It doesn't have any core. It doesn't have a holocore. It doesn't have a solid core. It has a regular periodic lattice of hollow channels. These dots are the hollow channels, and in between is the glass. So there is no core. So if this fiber were not twisted, you wouldn't expect to see any guiding of the light. The light would just leak away. But when you twist it chirally, and this is done by spinning the preform during fiber drawing, it actually turns out the fiber can guide light. And these are experimental measurements of the mode field pattern that you see in experiments. As the twist rate, this is a radians per millimeter that represents the twist rate, as that increases from 1.26 and up to pi, the mode diameter shrinks as the twist rate goes up. So it's definitely related to the twist that we get this guidance mechanism. And then you can run some numerical experiments on a computer, and we got very good agreement between the experimental measurements and the simulations. So that's the results, and it's a curious kind of it's a curious phenomenon, unexpected perhaps. So let me explain how we believe it works, or at least how we like to explain this phenomenon. Let's first think about an untwisted coreless PCF. And this is a simple depiction of the refractive index distribution across the fiber. So this is the axis of the fiber. This is refractive index in the vertical axis. So we jump from silica down to air and up to silica and so on as we cross the structure. And if you work out the photonic band structure of this periodic structure, you're going to find that there's the well-known cutoff region above which light can't propagate. We then have a pass band where the light is able to propagate freely through the structure. And then we find we will hit a photonic band gap, typically at lower refractive index, and maybe another pass band. And as you reduce in refractive index, you get more and more complicated features in the band structure. But we're mainly interested in this first pass band and the first photonic band gap. Now, that's the straight fiber. So what happens when we chirally twist the fiber? Well, what happens is that light that is trapped, let's say, in this glass strand in the cladding, of course, it's not perfectly trapped, but it will be bound to a degree. It will be somewhat leaky, but there will be a blob, if I may call it that, a feature, a light feature that is trapped in the silica strand. When you twist the fiber, that piece of light, that spot of light is forced to describe a helical path. So here it goes in a straight line, and here it goes around a helical path around the axis. So this means that the geometrical path length is increased for light, say at this position. And as you change the radius, the geometrical path length increases as the square of the radius, the square of the distance from the axis. So we get a quadratic distortion in the whole band structure of the system because of this. And I emphasize this is a purely geometrical effect. It's a property of three-dimensional space, which is chirally twisted. And in both the group velocity and the phase velocity are reduced by this effect as you move out to higher values of radius. So let's just think a bit more about this. Let's zoom in to the passband, and let's think about we're going to set the effective axial refractive index. That'll be the modal index. We're going to look for guided modes in this system. So we need to set a certain refractive index, and then think about what happens as the light moves across the fiber structure. So if you're near the top of the passband, the light can always refract outwards. There's no mechanism to keep it confined near the axis. It'll just keep refracting outwards and leak away if you're close to the top of the passband. But at the bottom of the passband, the light can certainly leak away from the axis, but then it hits the photonic bandgap and gets kicked back. It gets reflected back, and it goes back again, and then it hits the photonic bandgap, gets kicked back. So we have the mechanism for a trap, where we can keep the light trapped inside close to the axis. And this is indeed where the guided modes form in this twisted structure. And I'm going to sort of attempt to animate how this works for you. So this curve here, this blue curve is the dispersion surface, you can call it that if we like. And I'm going to just reproduce this here as this is the quadratic dispersion surface that you've kind of seen in the system. So here we have a photonic bandgap. This is the transverse wave vector. This is reciprocal space. So now we're plotting the band structure. This is the axial wave vector. This is the transverse wave vector. And we have the dispersion surface that has this kind of shape. And now this is real space. So at this particular point, which is on the axis, the light is going to be sitting at this point on the dispersion surface. And by the way, the group velocity points normal to this dispersion surface. So at this particular point, the group velocity points that way. So it points along the ray path of the light in the twisted fiber. And then as we move out to larger values of radius, the whole dispersion surface moves upwards. And let me just animate this for you. So I think you could, I'll stop this in a minute, but this is basically what's going on. As we move out in radius, the band structure moves upwards, the photonic bandgap moves upwards, and when the light touches the photonic bandgap, it gets turned back towards the axis. So if I just stop this, and I'll just say stop at this point. Now the light has hit the photonic bandgap, it gets turned around and goes back. And then if I go further, the bandgap drops again, and the light speed are propagated, crosses the axis here. And then when it crosses the axis, it finds the refractive index is going up again, so it comes down again. And you basically have a system, a means of trapping light near the axis of the fiber. And of course, you'll find that modes form at certain values of refractive index when you apply phase condition and so on to this. Okay, so these are pictures. Oh yes, so that's an explanation of how this works. Another interesting feature of this is that if you do the theory of this is available in this paper, but if you calculate the ray path, and you can do this analytically using Hamiltonian optics, you find that the effective mass of the light is negative at the bottom of the passband here. So this has an interesting consequence, which is that when you bend the fiber, normally when you bend a fiber, you expect the mode to move to the outside of the bend. And this is well known. It's like a centrifugal effect where the light gets pushed away towards the outside of the bend. So you get a distortion in the mode shape. But in this case, because the effective mass of the light is negative, it gets pushed towards the inside of the bend. So this is an experimental result. The mode would normally be sitting in the center of this plot, but when you bend the fiber, it moves, the light moves towards the inside of the bend. And we confirmed this with theoretical simulations as well. So it's kind of an interesting aspect of this guidance mechanism. Okay, something else. Now, this also has to do with chiral fibers. This has to do with vortex modes that carry angular momentum, orbital momentum, and so on. And in particular, I would be very interested in N-fold rotational symmetric multi-core photonic crystal fibers, and what I like to call helical block modes. These are modes that are periodic in the azimuthal direction around the axis. So the type of structure I want to talk about is a six-fold rotationally symmetric structure with 6 cores. As you can see, this is a scanning electron micrograph of the fiber structure with 6 cores around the axis. And we may make straight versions and twisted versions, and we compare them and so on. Now the thing about if I start the animation here, if you imagine there is a mode in the structure, the mode will be guided in the cores, of course, and because they're quite close, the modes can couple to each other, the cores can couple to each other and form a kind of super mode of the system. And if you excite one of the super modes in the straight fiber, it will just go along without change. But in the twisted fiber, it's forced to rotate as it travels along. And because the cores are far away from the axis, the effect of this twist is quite strong. I mean, you get things like circular birefringence and all kinds of other effects. So I want to talk about the properties of the modes of a 6-core fiber like this. But first of all, I'd like to look at the straight case and talk about the kind of modes that will form in this structure. Now, if you do a standard coupled mode theory of this, I mean, this is what most people would do. You know, you're presented with 6 cores in a ring. You're asked what are the modes of this 6-core system. Well, certainly the first thing I would do is reach for scalar coupled mode theory. So you just let the cores be coupled to each other, nearest neighbor coupling, and you'll find that you get a mode with the lowest refractive index, which looks like this. This is the highest order mode of the system, where the phase flips plus minus around the ring. You'll also find that there's a mode with the highest refractive index, which is like the fundamental mode in which all the cores are in phase. And then in between, you find these curious modes where the light is only present in 4 of the cores, and the other cores are dark. And another version of this, which is this one. And just looking at this, it's pretty clear as to why this is so, because if light couples from plus to this core and minus to this core, they're going to cancel, so you can't have any light in these 2 cores. And the same thing is true of this case, where it's plus in this case and minus. Now these pairs of modes are degenerate. They have exactly the same refractive index. Well, that's kind of obvious because they are basically the same mode. And it turns out that if we superimpose these 2 modes with the third version of it, because there are going to be 3 versions of this, obviously, there's going to be a third one too. If you superimpose them with the correct phase difference, you can create a helical block mode that carries azimuthal momentum. Just let me show you how this works. So let's take the one with plus and minus, and we rotate it 60 degrees, and we add it with a phase difference, e to the I pi over 3, and then we add the third version of this with e to the I 2 pi by 3, add all these 3 up. When you do the calculation, you find that you get a mode that looks like this. There's light in every core. Now but there is a phase progression around the ring. So in other words, by superimposing these 3 degenerate modes, we create a mode that carries a vortex, an optical vortex. And we can take the other mode, which is plus minus. This is plus minus version. And this time we put in 2 pi over 3 and 4 pi over 3. And we get a mode. These look exactly the same, but there's an underlying phase progression around the ring which makes them different. And in fact, if you look at the topological charge, which is the number of phase singularities on the axis, these 2 modes will have a topological charge plus and minus 1, and these ones will have topological charge plus minus 2. Okay, so that's 6 cores, and actually sometimes we're interested in a large number of cores. The trouble is this procedure is very hard to use if you have a large number of cores. It gets very, very complicated. And there's actually a much better way of doing this. This is to use block waves. So to explain this, I need to tell you a little bit about Bloch waves. I know some of you know all about this, but just to make sure everybody understands, let's discuss a system of parallel waveguides, an infinite number of parallel waveguides next to each other, and we think about the nearest neighbor coupling between the cores. So we have nearest neighbor coupling, and this would mean that the amplitude in the nth core would say be an. The rate of change of that with distance is going to be given, well, for an eigenmode, it's going to be a constant times, it's going to be I gamma times an, so that would be the eigenvalue of the mode. And this will be then coupled to the nearest neighbor modes, an minus 1, an plus 1 with a coupling constant. We then apply Bloch's theorem that says that the phase between successive cores will be exactly equal to the Bloch phase. So we can replace an minus 1 with e to the I phi b and an plus 1 with e to the minus I phi b. You add them up and you get a cosine. So we can calculate the eigenvalue, the gamma value, as a cosinusoidal function and plot it out. So this is now a plot of the axial propagation constant of the Bloch modes, and this is the transverse propagation constant of the Bloch modes, and it's a sinusoidal surface, and this is the first Brillouin zone. And you can tell all sorts of things about these Bloch modes. The most important thing for this talk is that the direction of the group velocity points normal to these dispersion surfaces, as we call them, the dispersion surface. They point normal to the dispersion surface, so we get some feel for how the energy is flowing, what direction the power is flowing in the system. Okay, so what's the link between this and this 6-core fiber that I was telling you about? Well, it turns out that we could just take, if we just take six periods of these cores, and then we wrap them around in the cylinder like this. So we join this edge to this edge by wrapping them around the cylinder. We end up with a 6-core system, and we have the same dispersion surface as before. Of course, because this is now a closed system, the Bloch wave vector that's propagating around the ring, it can only take certain values. So only certain values of Bloch phase are allowed because of the closed azimuthal path. In other words, the n times the Bloch phase, which is the phase difference from one core to the next, n of those, which will take you once around the ring, has to equal a multiple of 2 pi. And this is then the azimuthal order of the system. That has to be an integer. So if we plot this dispersion surface versus azimuthal order, we can only get certain values of azimuthal order, and these would represent the Bloch modes of this system. So they're going to be, you've got 6 cores, you'd expect it to be 6 Bloch modes, and this is a scalar model, by the way. So this all works. This is all fairly clear. So I think, but of course, light is not a scalar. It's a vector field. We need to, in general, do a vector coupled mode theory. This is not so difficult to do in practice. So in order to do this, we need to specify, say, a radial component of electric field and an azimuthal component of electric field, and use cylindrical coordinates because this reflects the symmetry of the system much better. We can then resolve the fields along a line joining 2 of the cores. We need a rotation matrix to rotate the fields along this line. We need a coupling matrix, kappa or k, and we need to rotate back again. And it turns out that the equation, the coupled mode equation, the vector coupled mode equation takes this form, where these are the 2 coupling terms. They now have rotation matrices. Everything's vectorial. We could then apply Bloch's theorem just as before, and you can end up with an analytical form for the modes that form in the system. And by the way, you can also treat birefringent cores if you want to. So, okay, so there isn't time to go into a lot of detail here, but let me show you the results. So when you actually run this analysis, this again is for a straight fiber, it's not twisted. What we find is that the dispersion surfaces separate out into the spin -1 and the spin +1, so left and right circularly polarized modes. They're perfectly circularly polarized when you do this analysis, and you find that one of the spins is displaced by 1 from the axis. So whereas the scalar, the scalar case looked like this, there was a single curve But when we do the vector case, we find we get two curves, and they're displaced by one from the position of the scalar curve. And actually, this is kind of for this straight fiber, the azimuthal order +1 and spin +1. If we instead of using azimuthal order in spin, you can translate that into topological charge. So topological charge is the azimuthal order minus the spin. Okay, so if I take the mode that has azimuthal order +1 and spin +1, that will have topological charge 0. So that this curve moves to the left, and we now then have topological charge 0, and that's a fundamental mode. And if I take the other one, so -1 and spin -1, again you get 0. It moves towards the right, and we get to topological charge of 0. And the other modes will give you other values of topological charge depending on where you're actually sitting. So we can plot this versus topological charge. This only works for circularly polarized fields, because if they're not circularly polarized, then S is not exactly 1, so you can't do this. So this looks exactly like the scalar case. If we go back to what I showed you before, I mean, this is the scalar case. You get a single sinusoidal curve, and in this case, we get a single sinusoidal curve as well. So what about the twisted fiber? Well, it turns out that we can handle the twisted fiber, at least to a first approximation. We can simply tilt these waveguides, and this means the band structure tilts as well. And if you do a very careful analysis, you actually need to use a Frenet-Serre approach to the system. This is explained it's explained in this paper here, which will appear in Joseph B fairly soon. It turns out the curves look like this. So again, the red and the green curve, they're now tilted because of these waveguides being tilted. So basically, we take this and we wrap it around the cylinder. We end up with something that looks like a twisted fiber. It's not quite as straightforward as that. For these dispersion surfaces, the dispersion surfaces look like this. So the tops of the dispersion surfaces actually are at the same position, but they're both tilted. And once again, for circularly polarized fields, we can just move them on top of each other and plot against topological charge in this system, and we end up with the 6 modes again. It looks like the scalar case. But what's interesting in the twisted fiber is that these modes are no longer degenerate. So +2 and -2 are no longer degenerate. In fact, all these modes in general, they have different propagation constants. So they all become non-degenerate, whereas before there was lots and lots of degeneracy in this case. Where lots of the modes have the same propagation constant. In the twisted fiber, this is no longer the case, and this turns out to be very useful. So let me show you some experimental results. So these are experiments on a 6-core fiber, 6-core ring. And these are the modes that we measured in the lab. So this is the topological charge -2. It has 2 spirals in the pattern. In fact, we're sitting at this point, topological charge -2, circularly polarized fields. Topological charge -1 is now this point. It has a single spiral, as you'd expect, because topological charge, and this is the number of phase progressions 2π when you go around the ring. And then we have +1, and we have +2. They're rotating in the other direction, of course. Now, these patterns are formed by interfering with a divergent Gaussian beam, the common technique for visualizing the azimuthal phase progression of the field. There's just one other interesting thing about this, about these measurements. As you can see, there are phase singularities, these kind of forks in the interference fringes at different positions away from the axis, from the center of the fiber, and these are actually caused by harmonics of the Bloch waves, the Bloch modes. Because this is the first Brillouin zone. There's also going to be, so at this point, there'll be a point in the next Brillouin zone that has a value of not 2, but actually 8. So it's 6 + 2 because of 6-fold symmetry. So you can actually get lots and lots of other phase singularities caused by the higher harmonics. And you're seeing evidence of these in these patterns. Of course, they're not perfect because this is an experimental result, but it's quite interesting, I think. Just to show you, it is actually possible to come up with a analytical dispersion relation for these complicated sounding modes. And this is the expression that one gets. And the reason I'm showing you this is to show that, actually a very important point, which is that the index of the nth harmonic, so of the block mode, of the helical block mode, it depends, this refractive index depends on the topological charge and on the spin in general. And then if we look at the actual expression, here's a term that describes the quadratic change in refractive index with radius. This is a term that describes the slope caused by the twist. Alpha is the twist, 2 pi over the helical pitch. This is the topological charge. Here we have a term that involves the spin, which is interesting. I'll come back to that in a minute. Then we have another term. It has the coupling constant. It has, again, this square root function caused by the quadratic change in path length with radius. And inside here, we have the topological charge again. So this is kind of the dispersion surface, the cosinusoidal dispersion surface. So all the terms in this expression, they only depend on L, the topological charge, except for this term. And this term, sorry, this term contains the spin. And actually, when you look at the value of this number, it's actually very small compared to all the other terms in the typical experiment. But there is a very small amount of circular birefringence in the system caused by the twist and the fact that the radius is not 0, because you're off. If the radius is 0, this term goes to 0. But because the cores are away from the axis, you actually get some circular birefringence as well in the system, which actually turns out to be very useful in some cases. So this is all in that paper if you're interested in looking into it in more detail. Okay, so next topic, and this is probably a little easier to follow. I realized that was quite heavy as a topic to understand all the different details. But now I'd like to talk about these recent anti-resonant reflecting Holocore PCFs, these simple single ring fibers. These anti-resonant reflecting fibers, and they date back, as I said, to 2002 with the very first Kagome fiber, which turned out to guide quite light, which was quite unexpected at the time. So we didn't fully understand why this was so originally, but we began to understand that it had something to do with the first row of hollow channels around the core, that this was key, because there wasn't any photonic bandgap in the structure. It didn't have a photonic bandgap, so why was the light confined, and why was it broadband? It turned out to be the first ring of hollow channels that was really key. And then a group in Moscow came up with this structure of a ring of capillaries and reported that they could get guidance in this core. I mean, the losses were quite high, but that was the first example of a fiber like this. This was a structure from the group in Bath, Jonathan Knight and his colleagues, which gave some very nice guidance in the infrared. Again, a very simple structure. This is a paper from the groups in France, Fede Benabid and his colleagues. This is a structure that we worked on some years ago. Again, a single ring of capillaries around a hollow core. Some more complex structures from a group in China. And then Southampton's also been getting into the field in recent years as well, and achieving extremely low loss. So it's very exciting to see how low the losses can be. I mean, we're talking of losses that are getting down towards a dB per kilometer, or possibly even less. They may even challenge telecommunications fibers at some point in the future. But I'm not talking about telecoms here. So why is the guidance so broadband in these fibers? Well, the reason for this, you can explain it fairly straightforwardly. So let's suppose we have a core mode sitting in the center. The solid is guided nicely by anti-resonant reflection. It's unable to get into the capillaries because it's not resonant with the capillaries. If I plot out the refractive index against wavelength of that core mode, it's going to have a curve that looks something like this. It's an 88 micron core. If I now think about the modes in the capillaries, these also have a dispersion that's quite slow with wavelength. It's a little bit faster than the core because these capillaries are smaller, but it's nevertheless very slow. And there's nowhere where these two modes can actually cross and couple to each other, be phase matched to each other. So in other words, if you have if these modes are dephased, they be dephased at pretty much any wavelength, and you should get reasonably low loss. It's never going to be completely zero loss, but it'll be much reduced leakage loss. And if we look at the actual dephasing length for these two modes in this particular case, so this is the length over which these two modes dephase from each other. You want that length to be as short as possible. We find dephasing lengths in the millimeter range over this entire wavelength range. So these modes will dephase over a few millimeters, so they don't have much chance to couple to each other, and so you don't get much loss. But another aspect of these fibers is that the thin glass walls of the capillaries also support resonances or modes. And in fact, they would guide properly guided modes. If you just launch light into them, you'll find there's a guided mode. And then as you change the wavelength of that guided mode of a higher order mode such as this with two lobes, you reach a point where that mode cuts off as the frequency drops, and the mode cuts off and it starts to leak. And at that point, it can start to couple very strongly to the core mode. And in fact, if we plot the dispersion, refractive index versus wavelength for these modes in the glass walls, the curve is incredibly steep. So we get two anti-crossings very close to each other, anti-crossings both with the core mode and the capillary mode. So in this wavelength range, close to the crossing points, we get huge loss. You get massive loss. But provided you operate away from those points, you can actually get quite very nice guidance in the fibers. And one other thing that turns out to be useful and actually very simple is a way of avoiding. Sometimes you'd like to just have a fundamental mode on the core and not have any higher order modes. Higher order modes are sometimes a nuisance. You don't like to have them. You'd like to have a single mode fiber or an effectively single mode fiber. This can be arranged just by adjusting the ratio between the diameter of the capillaries and the diameter of the core. If you arrange that to be a ratio of zeros of Bessel functions, 0.682, then you can get extremely high loss for the high order mode, and the other high order modes are much higher loss anyway. So you can then end up with a Holocore fiber that has essentially single mode, that gives you single mode guidance. And for some applications, that's actually very, very interesting. For example, if you want to transmit ultraviolet light in a very nice fundamental mode without any distortion, this turns out to be an excellent way of doing that. Okay, so this is a race through a lot of different topics. So my next one, well, it's linked to Holocore PCF, and it's linked to the single ring Holocore fibers I've just talked about. And this is another curious phenomenon. It's the observation of circular dichroism in a twisted single ring Holocore fiber. Circular dichroism is something that's normally associated with molecules or some kind of complicated material. Proteins, for example, have circular dichroism. And of course, circular dichroism means that left circularly polarized light has a different absorption rate compared to right circularly polarized light. But in this case, the fiber is made entirely from glass and vacuum, if you like. So whatever is going on, it's just a geometrical effect. So let me show you the results, first of all. So we're working with a single ring fiber. It just happens to have 5 capillaries. There's no significance in the number 5. It just happens to be the fiber we were experimenting with. If we launched in left circularly polarized light, of course, it's a twisted fiber. For a certain sign of the twist, left circularly polarized light sees only the background loss, so we don't see any features in the spectrum over this range of wavelengths, microns, 1.55, 1.62. And if we launch right circularly polarized light, on the other hand, at this wavelength, we get about 8 or 9 decibels per meter higher loss for the right circularly polarized mode compared to the left circularly polarized mode. And in this case, what seems to be happening is that the core mode is coupling very strongly to the capillaries in this case, whereas in this case, it's not. And of course, in this case, if light gets into the capillaries, it will then leak away into the cladding, and you get lots and lots of loss. Experimental modeling, or I should say numerical experiments, confirmed these results. So now that's the observation, and it wasn't that easy to explain what's going on, but we succeeded in the end, and I'd like to explain how this works in practice. I might come back to that in a minute. So what is the mechanism of this? So let me try to explain this. So here we have axial refractive index on the vertical axis. This is azimuthal order of the modes. This is the number of cycles of 2 pi as you go around the azimuth. And this is within the first Brillouin zone of this five capillary structure. So it's got 5-fold rotational symmetry. The fundamental modes of the core will have azimuthal order +1 and spin +1, so that when you take LA minus spin, you get 0. So topological charge 0. So this is the fundamental mode spin +1, and this is the fundamental mode spin -1. Okay. So these fundamental modes will have a certain propagation constant, certain axial refractive index, and this is more or less unaffected by the twist. You know, you can twist the core mode is not much affected by this this effect. So let's now think about the ring of capillaries. So think about the mode in the ring of capillaries, and because it's a ring of coupled capillaries, we can use helical block theory that I just explained to you. We get these dispersion surfaces, and let me just do this. So in the untwisted fiber, so this alpha, this is the twist rate, is 0 in this case. In the untwisted fiber, we have these two, the green and the red dispersion surfaces, like you saw before, for left and right circularly polarized light. And it just so happens for this particular case, there is no phase matching between the core mode and the ring mode. So you'd expect to have reasonably low loss in this case. So as we change the twist rate, then these dispersion surfaces, well, they tilt and they undergo a kind of, because of the twist, they change their shape and they tilt. And then at some point we find at a magical value of twist rate, the green curve intersects with the S equals +1 core mode. But of course the polarization state of these two, of the ring mode and the core mode, are opposite. So you wouldn't expect, they're orthogonal in this simple theory. Those modes are, so they're phase matched, but they wouldn't be able to couple because they're orthogonal, at least in this simple theory. And then if we go to higher twist rates, we can actually find a point where this happens, and we get phase matching from the core mode to the ring mode with the same polarization state. But when that happens, you get exactly the same kind of phase matching for the other polarization state. So there won't be any dichroism in this case. Whereas if I go back to this case, we have phase matching for the S equals +1 core mode, but there isn't any phase matching for the S equals -1 core mode for this particular case. So we have the basis here for circular dichroism. In fact, this is what's going on in the structure, but what I haven't explained is why it is that these modes are able to couple, because they have the opposite circular polarization state. So why is that? Well, the reason is that this simple theory doesn't capture all the physics. And in fact, the field polarization state, when you look in detail at what's going on in the structure, the field polarization state varies spatially in the actual fiber. And this means that the core and capillary modes are not perfectly orthogonal. So you can get coupling here, and you can get very strong, much higher loss for that polarization state. So that's basically the story of the circular dichroism. And interesting effect, very difficult to explain, but I think we now understand what's going on. So something completely different, but also involving Holocore fiber, is another project within my group that's been running for a number of years, which is using laser tweezers to guide particles in Holocore fiber and then sort of do interesting things with the particles once they're actually guided in the Holocore fiber. And one application is flying particle sensors, those laser tweezers. This was the invention of Arthur Ashkin, who sadly passed away last year. He won the Nobel Prize towards the end of his life in 2018 for this work on laser tweezers. So let me just tell you just briefly about this work. So the idea here is that we have a Holocore fiber, and this could be hundreds of meters long. We have a system of launching light into the opposite ends of the fiber, and we have a means of launching small particles into the Holocore fiber using laser forces to propel the particle, and also trap the particle. Once it's inside the core, the particle will be trapped at the high intensity center of the core mode. So if we launch a particle, it will fly into the fiber. We push it along. You can monitor its position using laser Doppler effects, and then by adjusting the power balance between P plus and P minus, we can bring the particle to a halt at a certain position where we want to measure something. Once it's there, we could, for example, measure the radiation level. This could be some radioactive environment, and we'd like to know the radiation level there. This could be done through luminescence. So the fiber would capture the luminescence of a particle that was radioluminescent, and you could then detect the radiation level at the input of the fiber. We could also send in, we can also use the fact that the viscosity of the air that's filling the holocore fiber depends on temperature. So in other words, the velocity of the particle, if you keep the optical power constant, the velocity of the particle moves at depends on the local temperature. This gives you a nice way of measuring the temperature locally along a piece of optical fiber. And you could measure the temperature along the entire length of the fiber, and the particle comes out again. So it doesn't stay in the fiber. You can move it again afterwards. You could send in a charged particle and measure the local electric field. So if there is a local electric field, then it will push the particle sideways in the core, and this will change the transmitted intensity of the light. So you can monitor the local transverse electric field along the fiber. So lots of different things you can do with this system, potentially. So it's a new kind of optical sensor. It can have a resolution of a few microns. It's basically the size of the particle, and it's fully reconfigurable. You don't have to change the system if you want to measure different quantities. You just send in a different particle and then retrieve it afterwards. So something else we've been doing with this recently, and this is the work of Abhinav Sharma, has just finished his PhD with me. So this is a way of detecting these unpleasant PM 2.5 particles. I know that in many countries these particles are causing all kinds of health problems. India, I know, has problems with that, and certainly London has bad problems, and lots of different, China, I mean, all over the place, these particles are causing trouble. And they're very hard to detect. You can detect large particles very easily, but it's much more difficult to detect these particles that are smaller than 2.5 microns in diameter. So we came up with a way of doing this, of monitoring these particles continuously. And it involves a length of holocore fiber. And this would be the particles flowing into the system. You turn on the laser beam, just keep it on. And if a particle drifts in, gets captured by the laser beam, gets pushed along the holocore fiber, we can measure the time of flight that it took for the particle to travel along and the transmission drop, the drop in transmission. If a smaller particle comes along, it will travel more slowly, and the transmission drop will be less, and the time of flight will be longer. If, however, we have a high index particle, it will travel more quickly for the same size because the refractive index is higher. So we have we have these two independent parameters we can measure, the time of flight and the transmission drop. And it turns out with these two parameters, you can actually work out the refractive index and the diameter of the particle that is pushed along inside the fiber by the light. These are some of the measurements showing you the transmission drop in percents. Is quite small, but certainly easily detectable for different for polystyrene particles of different diameters. So as they get smaller, the transmission drop gets less, of course. For different materials, you can easily measure these parameters, these two quantities for any particle that you want to look at. You'll notice there's a lot of oscillations here in the results. In fact, this is caused by intermodal beating, so we didn't try very hard to prevent excitation of high order modes in the core, and then you get intermodal beating, and this causes this oscillation. But you take the average value, you can get pretty good measurements. And just to show you that this works, that you can actually read out refractive index and diameter from these two measurements. So the curves for constant particle diameter and constant particle index are almost orthogonal to each other. So this is the curve for these are the curves for constant particle diameter, 3 microns, 2.8, and so on. And these are the curves for constant refractive index. And they're almost orthogonal. And in fact, because of this, it's possible to distinguish polystyrene from silica particles in the experiments as shown over here. And just to show how this works, suppose we measure a time of flight of 0.2 seconds in this particular case, and we measure a transmission drop of just less than 0.3%. We can then read off from this chart the diameter of the particle, 2 microns, and the refractive index of the material 1.4. And this works really, really well. And what I find remarkable is that these curves are pretty much orthogonal, so you get an unambiguous measurement of refractive index and particle diameter, which could be very useful. Sometimes you'd like to know what these nasty little particles consist of, what material they are, and then refractive index is an important measure of the material itself. So my last topic, I'm not sure how time is going. I could probably doing all right. Has to do with something quite different that I haven't really touched on so far, and this is nonlinear optics. The Holocore fibers are wonderfully useful for investigating nonlinear, ultra-fast nonlinear effects in gases. And in particular, you can carry out extreme pulse compression, and as a result of that, generates ultraviolet light with high efficiency through something that's called dispersive wave generation. So let me just talk first of all about chromatic dispersion or group velocity dispersion of a holocore fiber filled with gas. So let's think about a hollow fiber. I mean, many of you will have analyzed microwave waveguides, hollow waveguides, different types of systems, and you'll know that it's very simple to calculate the refractive index of the modes guided in a hollow core. And in this case, where you find that for a hollow waveguide like this, the optical modes always have anomalous dispersion. That's to say the higher frequencies travel more quickly guided in a system like this, if this is full of vacuum with no other material. And this is a purely geometrical effect. It just has to do with the diameter of the core, or the ratio between the diameter of the core to the wavelength. And as that gets smaller, the anomalous dispersion gets stronger. If you think about a typical bulk material that has normal dispersion, then the bluer light will travel more slowly. The red light travels more quickly for a typical glass and say in the near infrared or the visible. And that's a material response, of course. Now, if we take the bulk material and put it into the hollow core, then the dispersion that you will end up with will depend, of course, on the relative strengths of the material dispersion and this geometrical dispersion caused by the hollow core. If the bulk material was a gas, and you could change the pressure of the gas, and maybe you could balance this anomalous dispersion against the normal dispersion of the gas, and come up with all kinds of different values of dispersion. And this is the essential reason why these holocore fibers are so interesting. I mean, well, there are several reasons. I mean, one is that you get very long, well-controlled path lengths. The light's kept beautifully confined in the hollow core over long distances. They permit broadband guidance, so you can guide a very broad spectrum of light. This allows you to have few cycle pulses. Turns out the optical damage threshold is very, very high as well. But the nicest thing of all, I think, about these fibers is that the dispersion is tunable. You can tune the dispersion by changing the pressure of the gas. You can make the dispersion anomalous if you want solitons, or you can make it normal if you don't want solitons. And here are some plots of how it looks. So this is dispersion, picosecond squared per kilometer. So anomalous dispersion is below the line here, and the normal dispersion above it. You can see that for an empty fiber with no gas, we have anomalous dispersion across the entire frequency range. And then as we add more and more, in this case, it's argon gas that we're adding to the system. As you increase the pressure of the argon gas, the normal dispersion of the gas counterbalances the anomalous dispersion of Holocore itself, and you can get all sorts of different values, different landscapes of group velocity dispersion as a function of frequency. So it's really the world's first fiber where you can actually adjust the group velocity dispersion to whatever value you want within limits, of course. One of the things about this is that by adjusting the dispersion and making the dispersion of the gas-filled holocore fiber, making it anomalous, you can guide solitons. And if you launch in a higher order soliton, fundamental soliton travels without change in its shape, but higher order solitons, they undergo successive cycles of extreme compression, and then they expand again, and they compress again, and they expand in a periodic fashion. Higher order solitons, you were in this case launching at a 30 femtosecond soliton. This is the time. This is the distance, the propagation distance. This is the spectrum and the time, temporal profile of the pulse. The soliton compresses in time down to a very small duration, and the bandwidth becomes extremely large here. And at this point, at this temporal focus, you can see the fiber is lighting up with some interesting bluish white light. I'll come to that in a minute. But we get this massive increase in bandwidth. And of course, you need a very large bandwidth to get a very short pulse. It makes a lot of sense. But then we also notice that there's a lot of light generated at very high frequency, in fact, deep into the ultraviolet. And this is caused by a phenomenon called dispersive wave generation. I haven't time to explain that today, but you can look it up. There are lots of papers on it. We get up to 10% conversion from the compressed soliton to this dispersive wave. And the reason this is all happening is that when the bandwidth becomes enormous, all the usual approximations used for solitons break down, because the light is now in a region of normal dispersion, so you don't get any solitons. It's partly why it's called a dispersive wave. There are no solitons here, so the pulse is just dispersed. So, and you also get soliton fission. There's all kinds of higher order nonlinear effects that happen at this temporal focus that give rise to this generation of a deep ultraviolet dispersive wave. Now, this technique of compression is extremely convenient for producing few cycle pulses, and you only need microjoule energies. This is 1,000 times less than is typical in most of the big labs that have done pulse compression previously in gas-filled capillaries, where the bore is very, very large. They need to use millijoule energies, not microjoule energies. There's an absence of damage in the fiber, which means you can get to very high intensities. You can actually study ionization effects as well as you want. But the thing that's most interesting in terms of applications is that we can generate wavelength tunable deep ultraviolet and vacuum ultraviolet light through this dispersive wave generation. And if you do a lot of careful experiments, as Kafai Mak, who has left the group for some years now, he's in Munich. He was a PhD student. He did a whole series of very careful measurements of this dispersive wave generation. His goal here was to generate narrowband radiation at a whole lot of different wavelengths, all the way from the visible to the vacuum ultraviolet, using different gases and different pressures and different fibers. He was able to get between 1% and 8%, sometimes even higher than that, conversion from the near infrared pulses going in to the ultraviolet light. And another student, Alexei Ermolov, pushed this work towards the vacuum ultraviolet. Working in the vacuum ultraviolet, as the name suggests, is not so easy. Because vacuum ultraviolet light doesn't propagate in the atmosphere, so everything has to be done in vacuum. So you need a system with a chamber that you can pump out to low pressure, and take the radiation from the fiber and do all the measurements in vacuum. And here he shows here's a series of measurements in neon gas, which went right down to about 140 nanometer wavelength. Neon gas is a lighter gas. It has a higher ionization potential. We want to avoid ionization in order to generate this light, so hence the choice of neon. And going to an even lighter gas, which is helium, he was able to get right down to close to 110 nanometer wavelength using helium. These are dispersive waves as before, but generated from infrared pump pulses. So this work is now actually being commercialized in various places because it's a completely unique source of bright, short pulses of vacuum ultraviolet and deep ultraviolet light. This is my last little topic, has to do with Raman scattering. So rather than using noble gases, so far I've told you just about argon gas and xenon and neon and helium and so on. But if you use a Raman active gas, that's a gas that has internal modes of motion, internal degrees of freedom, as we call them. So there can be vibrational degrees of freedom for hydrogen gas working with hydrogen. You get vibrational ones that run on 125 terahertz. There's also rotational internal motion of the molecules that run at 18 terahertz. This is a lower frequency. This is a much higher frequency. And the gain for particularly vibrational Raman scattering in hydrogen has the highest Raman gain of any gas. So it's a very good choice. It also has a very high frequency, which means that you can, with Raman scattering, you can translate the frequency of laser light by a very large amount, by 125 terahertz. And once you get, you got millions, billions, trillions of these hydrogen atoms that are vibrating or rotating. If you can arrange them that they're doing this in synchronism, then the collective molecular motion of all these molecules that are in synchronism with each other, it can act as a terahertz phase modulator for light that comes all along afterwards. So you send light through the phase modulator, you can then phase modulate the light at these frequencies, at these very, very high frequencies. So I was going to tell you about the work of Federico Belli, another PhD student who left us a few years ago. He did a lot of work on exactly this topic. So he used the pulse compression physics that I've told you about to expand the spectrum of a soliton. You send a soliton in. This is the anomalous dispersion region. You're sending a soliton is 532 nanometers, I think, in this case, or thereabouts. So maybe it's 800. I think it's 800. Yeah, 805 nanometers. And you see the soliton self-compression. The bandwidth grows. It gets really huge. You get this enormous bandwidth. The pulse gets very short at this point. And it gets short enough, and I'll tell you a little bit more about this in a moment, but this is a picture of the fields at the temporal focus where the bandwidth is the largest. So you get this very complicated kind of field, and this is the actual field of the light calculated. You get features that are really very, very short. In fact, they're so short that they're shorter than a half cycle of the vibrational motion, which means that the Raman, these oscillations in the molecules can be driven impulsively. It's like you hit a bell with a hammer, it will ring. If you hit it with something soft, you won't get anything. But if you hit it with something very sharp and very short, you get a nice vibration in the bell. And the same thing is happening with these molecules. And in fact, the results of this are quite dramatic. I mean, because these very sharp, short features in these very, very short pulses that are able to impulsively drive the Raman, the molecules then end up vibrating, as you see here, and the light that's left afterwards is phase modulated by these molecules. And in fact, we see in the spectrum, this is the spectrum generated in this system, because it's been optimized to give you a very broad band spectrum, not just a narrow band spectrum, but a broadband spectrum. We see, first of all, a dispersive wave at just below 200 nanometer wavelength. And this dispersive wave is modulated by the Raman vibrational motion to give you sidebands. And this sideband is the interesting one. This takes us way down into the vacuum ultraviolet. So it extends the spectrum that you get. Just to illustrate this, here's a series of plots of the pulse shape as you approach the temporal focus. So the pulse is sort of beginning to focus here. So this is impulsive excitation at this point of rotational motion. So the half cycle of rotation mode is 28 femtoseconds. And here we have the pulse is compressed down to a duration which is short enough to start to excite the vibrational motion of the molecules. This represents the vibrational motion of the molecules. Sorry, the rotational motion of the molecules at 18 terahertz. And then as the pulse gets shorter, it's down to 9 femtoseconds. In these two cases, a half cycle is 4 femtoseconds. This is quite short enough, but you're beginning to get a little bit of a vibrational motion excited. And then here it's down to 3 femtoseconds, which is less than half a cycle. And we're beginning to see very strong excitation of the vibrational motion as well as the vibrational motion as well as the rotational motion of the molecules. And then finally, it goes right down to 1.3 femtoseconds. And here you get really get the vibrational motion is getting very strongly driven. And this orange curve is running at 125 terahertz. And it survives for a long time after the pulse has disappeared, but there's residual radiation left behind that is phase modulated by this molecular motion that gives rise to the extreme vacuum ultraviolet radiation that's generated in the system. Just to finally show you the results here, comparing a fiber that's filled with argon gas that has the same effective nonlinearity and the same zero dispersion wavelength. So for argon gas, these are the results. A little bit messy, but never mind. That's the argon results. And this is what happens when you fill the fiber with hydrogen to get the same values of nonlinearity and so on. And we get a big extension in the supercontinuum. There's a big spectral extension towards the vacuum ultraviolet as a result of using hydrogen, as a result of the of the Raman phase modulation that you get through impulsive excitation. Okay, so that was the topics. I'm going to show you a list of all the topics in a minute, but first of all, let me just acknowledge all the people. This is a picture of my group back in July 2019 at one of our group retreats. Sadly, we haven't had any since then because of coronavirus, but just to acknowledge the people, this is the ultra-fast team, works on gas-filled fibers, Malika Suresh, Johannes Köhler, Alexei Ermolov, Francesco Tani, who's the head of the team, Daniel Schade, and Felix Kötig. That's the biggest team we have, I think. This is the team working on chiral PCF, on the twisted fiber. Gordon Wong is the head of that team. Paul Roach just finished his PhD. Yang Chen's a postdoc doing numerical modeling for us. Particle guidance work led by Shangran Ji, who's gone back to China now, starting his own group. This is Abhinav Sharma, who has worked on the particle guidance experiments. Optomechanical mode locking of fiber lasers that I mentioned at the beginning. This team was led by Meng Pang. He's now back in China. And the current leader of the team is Wenbin He. He's the guy here. And Jiapeng Huang, Donghan Ye, and so on are the optomechanical guys. And finally, last but far from least, are the fiber fabricators. It's Michael Froz, who's the head of the team, the fiber fabrication team in the Institute, and Jin Jiang, the two of them lead all the fabrication work. So that was the topics. I talked about optoacoustically mode-locked soliton fiber lasers, Vortex block modes, guidance in twisted coreless fiber, anti-resonant reflection, Holocore fiber, strong circular dichroism, flying particle sensors and devices, and extreme pulse compression and gas-filled fibers. That's a lot of topics, and I hope it wasn't too much for you. But as I said, I do have a PDF of the slides. If you'd like a copy, I can send that to you after the talk. So that's it for the moment, at least. Yes, I hope you're still there.
Thank you very much. It is exciting, and more than an hour you are speaking. So,
was I?
Yeah.
Oh dear, I'm sorry. Was that too long? Yeah.
No, it's okay. We are all enjoying. We are all following you. So okay. It is very exciting. So there are a few questions in the chat box. Shall I read those questions?
Yeah, sure.
Professor Balaji Srinivasan, he was asking that what about the surface defects on the glass wall? Don't they contribute significantly in the transmission loss?
What about the what?
What about surface defects?
I didn't understand that.
Surface defects.
I still didn't understand the word. Could you spell it out?
What about surface defects?
Oh, phase effects in what?
On the glass walls.
Oh, phase. Yeah, sure. Yes. I mean, if Let me just go. I mean, if we just go to that picture of these, yeah. I mean, if you happen to be exciting the system at one of these anti-crossing wavelengths, where the core light is strongly coupled to the glass walls, then the intensity in these glass walls will be very high, and yes, you can get very strong nonlinear effects as a result of that. But typically, we don't operate near these. We don't want to operate near these high loss, these high leakage loss regions. But yes, if you do operate near these points, then you'd expect there to be some nonlinear effects, some self-phase modulation, I would guess. But it's not something we've explored. We're actually more interested in the effects of these anti-crossings on the dispersion of the light at other wavelengths. So if you're operating at 1.5 microns, for example, if there's a very strong anti-resonance, if there's a very strong absorption line here or leakage at this point, this will affect the dispersion at 1.5 microns and actually can quite significantly change the dispersion of the system and therefore change the nonlinear properties of the pulses or the dynamics of the pulses as they propagate through the Holocore. Yeah.
Okay. And one more question, that's how the guiding in Holocore PCF affected by the bending of the fiber.
Oh, okay. So we're talking about these sort of fibers and how the loss is, how you get, what kind of leakage you get when you bend the fibers. Well, it depends a lot on the fiber structure. These very simple structures can actually be very sensitive to bend loss. So you do need to keep them quite straight. I mean, it depends a bit. I mean, if the core, it's the usual story. If the core is very big relative to the wavelength, you know, the Holocore itself is very large relative to the wavelength, then the bend loss can be really serious because a tiny bend will give you a phase difference between opposite sides of the core, and that kills off the mode, or you get a higher order mode and it leaks away. So it really depends very much on the design. But as a general statement, these very simple Holocore, these anti-resonant reflecting Holocore fibers, are more sensitive to bend loss than the photonic bandgap fibers. In the early experiments on the photonic bandgap guiding Holocore fiber, we had to break the fiber to get the light to stop being transmitted. It was extremely robust against bend loss. But these more these much simpler structures are more sensitive to bend loss. There's no question about that. Yeah, but not so sensitive that you can't think about using them in telecoms. So yeah, it's manageable.
Okay. Now one more questions. Can fundamental modes inside the 6-core fiber couple with second harmonic mode to make supermodes